There's Scott in his natural habitat.
Scout in his natural habitat.
Scott.
Make a mating call.
Do a bird call, Scott.
Can you pull that back blind open for me?
It's like a million birds.
Pull it up.
There's Philip.
Yeah, there you go. Almost.
Get Michael slacking on time.
Almost there. You.
There's Queen Kathleen.
Her face.
Not looking happy. Check 1, 2, and 3. Question. Nurse put their feet up on this desk and like started freaking out. What? In the world.
Okay, here's if we look at what we've surveyed with the galaxy so far. And by the way, these last 2 chapters here will have quizzes and such on them, and the information will be included on the exam if you have to take the exam. But there's not a test over these last 2 chapters. Anyway, they've figured out the distance to all these different galaxies, and they put a dot down. So our galaxy, the Milky Way, sits right at the vertex here. And this is just looking in a certain direction. I think it's a sliver of sky to the north. Every dot is a galaxy. And you can see this is that Great Wall that we talked about. It's basically the largest structure that we know about in the universe. And like I said last time, it actually comes out at you and goes into the board and forms kind of a bubble. And other than that, though, we don't see any structures greater than that. There's not any larger structures. And the reason why it looks like it kind of thins out here is just because there's probably a lot of galaxies there that we can't detect. But we say that the universe is pretty much homogeneous, which means the same throughout. Pretty much anywhere you look, it looks the same. So the universe kind of has a homogeneous look to it. There's not a lot more galaxies over here than there are over there. So we say the universe is homogeneous. Have you ever heard of Olber's paradox before? Olber's paradox says, people used to wonder, is the universe infinite? Does it go on forever? And Olber's paradox says, if the universe did go on forever, then wouldn't the sky be white at night, not black? And here's why he's saying that. Because if the universe went on forever, then no matter what direction you looked, your line of sight would eventually hit a star if the universe were infinite. That there would be a star eventually at any point you looked at. Kind of like if you're looking through the forest, your line of sight will eventually hit a tree if the forest is large enough. You see what I'm saying? So if the universe were large enough, wouldn't your line of sight always end up in a star or a galaxy, something that's bright? And if that were the case, the sky should be white instead of dark. That's Olber's paradox. Yeah.
What if it is and the light just hasn't reached us yet?
Well, that ends up being the reason why the sky is black. But why wouldn't the light have reached us?
They're moving away from the black hole.
If the universe were infinitely old, then the light should have reached us already. That's another thing that Olver was saying in his paradox. You can ask the same thing. Well, what the reason that the sky is black at night and not light is because the universe is expanding, you see. And remember Hubble's constant? The universe is expanding, and at 70 kilometers per second per megaparsec. Do y'all remember that number? What's that number called? Do you remember?
Hubble's constant.
Hubble's constant. Very good. And so if you take a megaparsec of space, a megaparsec is just a distance. If you take a megaparsec of space and you have a galaxy here and a galaxy there, those galaxies are going to be moving away from one another at a speed of 70 kilometers per second, which is pretty darn fast. So if these two galaxies were 2 megaparsecs away from one another, this galaxy and that galaxy are 2 megaparsecs away from one another, how fast are they going to be receding from one another? 140.
Very good.
Are y'all with me here? The further you get apart from one another, the faster the two galaxies recede from one another. Y'all see what I'm saying? 3 megaparsecs away, they're going to be going away from one another at 210 kilometers per second. Some of y'all aren't paying attention here. I don't think there's a way you can get this without thinking about it. So you could imagine if you put two galaxies far enough away from one another, they would be receding from one another faster than the speed of light. The speed of light is 300,000 kilometers per second. So if you put two galaxies far enough away, they'll be receding from one another so fast that the light couldn't possibly reach the other galaxy, because they're receding from one another faster than the speed of light. So the light is leaving this galaxy, it's going toward this one, but this one's moving away from that one, and the light will never catch it. So that's kind of what you're saying there, Michael. Light from the farthest galaxies from us can't reach us because of the expansion of the universe. The expansion of the universe expands faster than the speed of light. So you get a dark sky at night. Here's Olber's paradox. If you're on Earth, no matter what direction you look, it should hit a galaxy. However, the farthest away galaxies are receding so fast, their light won't reach us. Interesting little paradox. So, I talked about the Big Bang some the last chapters. The Big Bang says, because of this receding of all the galaxies, the Big Bang says that if you rewind that, there was a point about 13.7 billion years ago. You can round that to 14 billion years ago. There's a point where the entire universe started. And the universe suddenly, for some reason that we don't know, started to expand in size. So the universe started as a singularity. Singularity is a tiny point in space. An infinitely small point in space. Everything in this universe was once an infinitely small point.
Maybe black holes create universes.
Could be. And then that point expanded and expanded and eventually got to the size of that our universe is. And that's the Big Bang Theory. And it sounds ridiculous. The universe can't be as small as a single point. But black holes are the same thing. Black holes are an infinitely small point with tons and tons of mass, and we know they exist. So, that's what the Big Bang Theory is. It's also a TV show. So, there's a question, well, where was the Big Bang? A lot of people think about the Big Bang as a point in space, maybe way over there somewhere, that started expanding and stuff blew up into space, into the space that existed. But that's not the way to think about it, because we are part of the universe. Space is part of the universe. So, if we were in the universe, then if you rewind it and go backwards in time and the universe gets smaller and smaller, then space too gets smaller and smaller. And space will eventually collapse to that singularity if you rewind everything. So, you can't think about the Big Bang as happening somewhere out there and blowing up and stuff coming out into space. Space is part of the Big Bang. So, where did the Big Bang happen? It happened everywhere. Every part of the universe was at the point of the Big Bang at one time. And it's kind of counterintuitive. It doesn't make much sense. Here's another way to think about it. If you take a balloon and you were to tape a bunch of coins on the balloon and start blowing up the balloon, you would see the coins all move away from one another as the balloon gets bigger. And you can think of the coins like galaxies. Each galaxy is moving away from one another. And the rubber of the balloon is like empty space. And so space expands. The galaxies move further away from one another. And that's like the expansion of the universe. So, where did the Big Bang begin? Well, if you rewind this and make the balloon get smaller and smaller, eventually all the coins are going to be on top of one another. So the beginning of the Big Bang would be that stack of coins that you end up with as the balloon gets small, eventually smaller and smaller, infinitely small. All the coins are going to be stacked on top of one another. That's where the Big Bang started, where all the coins are stacked up. That's everywhere. The Big Bang started in every galaxy, on every point of space. This is Bill Nye talking to somebody about it.
General relativity had shown that space was weirder than anyone could imagine. Anyone but Einstein, that is. To gain a clearer understanding of this strange universe, astronomers needed more observational data. And that required larger, more powerful telescopes, like the one that led to our next great discovery. When the Herschels had finished their survey of the heavens in the 1830s, they had cataloged thousands of these beautiful but hazy objects, then called white nebulae. At the time, no one knew whether they were part of our galaxy or distant island universes like the Milky Way. In 1924, Astronomer Edwin Hubble was studying the stars in several of these nebulae using a 100-inch reflector telescope at the Mount Wilson Observatory in California. The telescope enabled Hubble to estimate that the galaxies were routinely many hundreds of thousands, even millions of light years away. Here were objects as huge and as populated with stars as our very own Milky Way galaxy, which is why we today call white nebulae galaxies. The more Hubble studied these galaxies, the more he became intrigued. At the time, scientists knew that a beam of light from a star appears as a different color on the spectrum. The color changed according to the motion of the star. A shift toward the blue end of the spectrum meant the star was moving closer to Earth. A red shift meant it was moving away. The amount of the color shift also revealed the speed of that movement. Hubble found that when he measured the distance of a galaxy, its spectrum almost always was shifting to the red. And something else. The farther the distance, the greater the red shift. In other words, the universe was expanding. It was an astonishing discovery with profound implications. Measuring backwards from the expansion, scientists found that the universe appeared to have a cataclysmic beginning, what one astronomer labeled the Big Bang.
So the Big Bang, it's not really a bang. It's not like an explosion. It's an expansion. It's like the blowing up of a balloon. It's just getting larger. And so most people think of it as a huge explosion, which it's not. You can also think of it, if you want it in 3D terms, like bread rising. Here's some raisin bread. And then it's small here. And as you bake it, it expands. And every one of those raisins gets further from one another. And so that's what the universe is doing. And if you could just back that up, all the raisins would be right on top of one another.
I hate raisins.
The scientists don't understand why it expands. There's an energy out there making it expand. It goes against gravity. Gravity, you would think gravity, Einstein showed that massive objects warp space and turn space in toward the massive objects. And that's what gravity is. It's space that's bent toward massive objects. That's why things fall to Earth. Einstein showed that in his equations. So, all these galaxies ought to make the bread shrink, not expand. Because the bread, all this area here is space. And space ought to be pulled toward the raisins, and you would think the whole thing would shrink. But it's not, it's expanding. And scientists can actually measure the energy required to expand the universe instead of shrink it. There's some energy out there that's causing the universe to expand and go against gravity. They don't know what that energy is. You know what they call it?
Dark energy?
Dark energy.
The dark side of the force.
It's the dark side of the force. And the dark energy is making the universe expand. And you can calculate how much energy that is. And it's a heck of a lot. It's a lot of energy. It makes up probably 75% or 80% of everything that there is the dark energy that's causing the universe to expand. So most of the energy that's out there, it's more energy than the energy that all the stars make combined. That all the energy going through space, all the heat and light and electromagnetic waves, if you add up all the energy that's produced by stars, it's way less than the amount of dark energy that's out there. They don't know what it is. So this is an interesting thing about the expansion of space. If you take this balloon, which represents the universe, and you draw a wave on it, and then you blow up the balloon, the wave will expand, and the wave will get longer, and the wavelength will get longer. And so, if you take the early universe, let's rewind the universe and go backwards in time and go back to when the universe was very small. Do you think it was hot in that universe?
Oh, yeah.
If you took all the galaxies everywhere and you compressed them into a very small space, think that would be hot? It'd be amazingly hot. It'd be so hot you would have radiation that's compressed. You would have real high, short wavelength, high frequency radiation. What do we call short wavelength, high frequency radiation? There's a name for that radiation. Gamma rays. The universe would be full of gamma rays. Even the matter, once you get it that hot, the matter itself breaks down into energy. And all you have, at early times, the universe was completely energy. Gamma rays, when the universe was very small. But the universe has been expanding for 14 billion years. And those high-frequency gamma rays have been stretched out over 14 billion years to these very long waves. What do we call really long waves? There's a name for those too. Radio waves. So as you stretch out these gamma rays, they form radio waves, and there are radio waves that are moving through space that are basically an echo of the Big Bang. They were waves that were real small, and then the universe expanded, and those waves have been stretched out, and you can hear them. You can actually see them and detect them. There's a couple of astronomers who discovered them that got the Nobel Prize that we'll talk about tomorrow. So that those waves exist at all is evidence for the Big Bang. That the Big Bang is real, was real. Okay, so what's going to happen to the universe?
It's gonna crush.
There's different things that can happen. If you think about the universe, it starts at a point, it expands. Is it going to slow its expansion and come back to a point? Scientists have a name for that. That would be called the Big Crunch. Perhaps the universe starts at a point, expands. If there's enough stuff in the universe, enough gravity, perhaps it slows down the expansion and makes it come back to a point and crunches together trillions of years into the future, back to a point. I kind of like that idea, because perhaps, maybe it's been just doing that, it goes poo, 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 and maybe it just does that forever. That's one idea. We call that the Big Crunch. A universe that does that is called a bound universe. It expands and then contracts back to a point. It will do that if there's enough stuff in the universe. If there are enough galaxies, if there's enough gravity, it ought to slow the universe and stop it expanding and make it come back to a point. If there's enough stuff in the universe. If there's not enough stuff in the universe, it won't do that. It'll expand and then go on forever. We call that an unbound universe. So it's got to do one of those two. There's actually one other scenario. It could expand and slow its expansion, but if it's exactly the right amount of stuff in the universe, it'll slow its expansion and approach a point of stopping. Wouldn't be enough stuff to pull it back, but it wouldn't be enough stuff to keep it expanding. It would forever be slowing towards a point of stopping, if there's exactly the right amount of stuff in the universe.
So what happens when you hit the edge?
There is no edge.
Okay.
You would think there's an edge, but since you're in the universe, you can't leave the universe. So
Fair enough.
this is something that's difficult to understand, and I don't exactly understand it either. But you kind of stay in the universe. There's no way to get to the edge of it. As a matter of fact, the equations show that if you take off in one direction in the universe, if it's a bound universe, that if you take off in this direction, you'll come back to the same point from the other direction. You know, if you're walking on the earth, if I set out from here and start walking with my huge steps, I can just walk through the ocean. I'll come back to the same point, right? We say the earth is a closed, bound surface. In other words, you can start walking that way and you'll come back to this point because the earth is round. If there's enough stuff in the universe and the universe is bound, you'll do that too. You'll go in this direction, you can take off in a spaceship in this direction, and you'll actually come back to the same point if you travel long enough.
So you're saying if we have good enough telescopes, we can see ourselves?
That would be correct.
Okay.
That's if the universe is bound. If it's unbound and we took off in this direction, we'd keep going forever in that direction, never come back to the same point. Because the universe would keep on going. You could never reach the edge. So either way, you could never leave the universe. Which I don't really understand completely. And there's a reason why I don't understand it. It's because no one really understands it.
And how do they make equations on it?
Somehow the math tells you that that's true. And I don't know how to do the math.
Yeah, that's it.
So, whoa.
Yeah, I don't know.
So we have this number. It's called omega naught. Omega naught is a symbol that stands for the amount of stuff in a universe. And if omega naught is equal to 1, if omega naught is greater than 1, that means there's so much stuff in the universe that we say we have a closed universe. And here's this lady, and she's shooting a flashlight, and in a closed universe, the light would eventually hit her from behind. Kind of like the Earth is a sphere. That's if the amount of mass in the universe is large enough, the universe will be spherical, and you'll take off from one point, and you'll come back to the same point. If omega naught is less than 1, you have what's called an unbound universe. which scientists say is shaped kind of like a saddle, not a sphere. And why is it shaped like a saddle? You can read the more precisely section on page 465. Let me know if you understand it, because I don't really understand it.
What happens if it equals?
If omega naught equals 0, equals 1, then there's exactly the amount of matter in the universe to make it what we call flat. And that's the amount of matter, that's what we would expect to see. If you go in a straight line, you'll continue on in that straight line. In a closed universe that's shaped like a sphere, if you shoot two laser beams, one in that direction and one in that direction, they'll take off and they'll eventually come around and come back together at a point. Just like if you took off in that direction on the Earth and that direction on the Earth and started walking, you come back to this point. And so you see they show these angles where they take off like this. Somehow you can form a triangle with 3 90-degree angles on the Earth. Did you know you could do that? If you start walking towards the North Pole, straight from the equator, that's a 90-degree angle. Walking towards the North Pole from the equator, that's a 90-degree angle. And once you reach the North Pole, there's a 90-degree angle to those points. On a closed surface, you can have a triangle with 3 90-degree angles. And that's true on the Earth, because it's a round ball that you're on. When you're standing on the North Pole, if you walk in that direction and that direction, you'll hit the equator. And the equator goes straight up, right? But the points meet. So if omega naught equals 1, then the universe is completely flat, just like we expect. And if you take off in that direction and take off in that direction, a triangle, the points of light will form a triangle with the sum of the angles 180 degrees. If it is not enough stuff in the universe, if omega naught is less than 1, then you end up forming a triangle of light with the 3 angles less than 180 degrees. And so the universe is shaped like a saddle. Isn't this stuff weird? It's mind-blowing stuff. So which is it? Which of the 3 do you think it actually is? I'll tell you what the measurements say. Go ahead and guess. What do you think the universe is shaped like?
Saddle.
So,
How many vote saddle? Raise your hand. So you think the universe doesn't have enough stuff? How many think it's shaped like a sphere and closed? That's the way I would like it to be.
I think it's flat,
You think it's flat?
like a piece of paper.
It would have to have exactly the right amount of stuff to be flat.
Just kidding, it's not flat.
Well, scientists find that it's flat.
Oh, yes, I was right.
If you add up all the mass of the universe, omega naught equals 0.02. That's just with the mass.
How do they know what the mass is?
You can add up all the stars and stuff that you can see.
They made a giant
They don't.
Figure out how much that would weigh.
And then how do they find how much of that weighs, like how many of those, what you can
Just
see,
guess.
would fit into the universe?
Well, they take a finite space of the universe and
Oh, that one's
see how
orange.
much is in this space that we know
1,005
about.
pounds?
Yeah.
And then
Sounds about accurate.
just multiply that out for the entire universe based on...
But how do they know what to multiply by?
I don't know. I'm not sure how...
And that's only on ones they can
Somehow
see.
they know. Anyway, if you add up the mass of what we can see, the omega naught is 0.02, way too low. But if you add in dark matter that you can't see, the omega naught jumps all the way up to 0.25, getting closer to 1. And then if you add in the dark energy, it goes all the way to exactly 1.
Thank you.
Which is a weird thing. Why would it be exactly 1? That's what we're going to talk about tomorrow.
That's weird.
Zeus.
You get a light farming